So welcome. We are already in lecture 10 of our introduction to quantum optics. And today we have a very interesting day because apart from finishing this chapter about interaction between light and matter, we are going to start one of the main chapters and the main reasons why quantum optics has kind of a special field for itself, which is the theory of open systems. And this is something very important that we will start today and we will continue with for the basically until the end of the course. So, but before we start with all that, let's finish the chapter about interactions between light and matter. And let me, as we usually do, let me review a little bit where are we. So I remind you that what we are doing at the moment is we are doing the quantum theory of a nonlinear process, a frequency conversion process that we call a down conversion. And this process consists in the following. So we have a dielectric with second order nonlinearity. And then when we pump it with frequency 2 omega 0, so when we shine a very strong laser, monochromatic laser at frequency 2 omega 0, then the nonlinear effects in the crystal can transfer energy from this beam at frequency 2 omega 0 into another beam at frequency omega 0. So at half the frequency, approximately half the frequency. And this process of transferring energy from a higher frequency beam to a lower frequency beam, that's what we call down conversion. And what we saw is that in principle, for down conversion to kind of start, we actually require a small spark, like a small injection at the down converted frequency in order for everything to start. However, this small spark doesn't even need to be another laser. It could just be fluctuations, either thermal fluctuations, so a few photons that are there because of temperature, or even more interesting, quantum fluctuations. And what I promised you, or what I told you, is that, well, we call this spontaneous down conversion. So whenever the field that we are amplifying or down converting, it's essentially vacuum or a thermal field, then we call the process spontaneous down conversion. And what I promised you is that this spontaneous down conversion has very interesting quantum properties. And this is what we will see today, that in particular, this allows us to create squeezed states of light. So in order to develop the quantum theory, what we did was very simple. We just took our definition of light-matter interaction within the dipole approximation, in which the interaction, it's nothing but the multiplication of the electric field and the polarization field. But the polarization field, in this case, we refer to the second order polarization, which is quadratic in the electric field. And in particular, we put the nonlinear dielectric inside an optical cavity. And in order to remove any process, any nonlinear process that is not the down conversion that we want to, we assume that there are only two modes in the cavity that play a role in the dynamics. In particular, one at frequency omega 0, which will be our fundamental or down converted mode with a certain polarization. And then another mode, which is close to twice the frequency of that fundamental mode, and that we can call the pump mode or the second harmonic mode, with orthogonal polarization. And this was just for simplicity. Then the relevant part of the electric field, we saw that it has two components. One component is related to the fundamental field at frequency omega 0 with polarization in the y direction. And we call A to the annihilation operator of this field, and the field itself, it's E0. And then we have the part of the field corresponding to the mode at frequency omega-2 with polarization along X, and then with an annihilation operator B. So what we saw as well is that then if we focus on these two modes, the free Hamiltonian of the system, so in the absence of any interaction, is just so the free motion or the harmonic oscillator kind of motion of the 0 and 2 modes, of the A and B modes. And if we take also a simplifying assumption that the only component of the nonlinear susceptibility that plays any role is the XYY. And again, this is an assumption that just simplifies the calculation that we are doing in class. But if you don't make this assumption, you get exactly the same, just with a different prefactor in the Hamiltonian. But if we make this assumption, then the second order polarization takes a very simple form. It's just the square, okay, of the fundamental field, of the fundamental component of the field, okay? And therefore, the second order polarization is proportional to A minus A dagger square, and it's proportional to the sine square of the set profile of the standing wave inside the cavity. Okay, then essentially, when we plug this in the Hamiltonian, in the interaction Hamiltonian, then what we got was the multiplication of this second harmonic or pump part of the field with the nonlinear polarization. And this brings us to a Hamiltonian that has a prefactor and then two interesting terms. So the first term, it's this integral here. And the second term is this operator here. Now, this operator here, we already saw that we can expand it in this way, in which we see that the processes that it is describing have different kind of energy conservation pictures. So in particular, there is a term in which you can remove a pumped photon and create two down-converted photons, and that process preserves energy conservation or satisfies energy conservation. But then we have other two processes in which the energy of, let's say, the input, it's different than the energy of the output, or it's very, very different by optical frequency standards. And therefore, all these processes are kind of suppressed by what we call the rotating wave approximation. So on the other hand, this integral here, at the end of the day, if you perform the integral, what you get is that it gives you a requirement for the interaction to be non-zero, which is this one in here, in which the only thing that you are asking, this is what we call phase matching, and this is equivalent to a conservation of linear momentum. So in particular, this expression here is just telling you that you need that the momentum of the pump photon, which is h bar k2, but multiplied by the refractive index in the material, it has to be equal or approximately equal to 2 times, okay, the momentum, the linear momentum, which is h bar k0 times the refractive index of the down-converted photons. And then with this, when this condition is satisfied, and we also optimize the geometry of the cavity, then we get a contribution of this integral, which is just proportional to the length of the width of the nonlinear material, okay? So when we put everything together, and this is where we finished, then essentially the quantum Hamiltonian describing a down conversion, we can write it in this way, in which we have a mode at frequency omega-0, a mode at frequency omega-2 that we will assume is close to omega-0, and then we have this kind of term in here, in which you can create or annihilate down-converted photons by pairs by annihilating or creating pump photons, and with some kind of prefactor, and this prefactor, we call it G naught, and it's essentially the down conversion rate. So this tells you how much or how often, okay, this down conversion takes place. So how often a pumped photon is converted into two down converted photons. So essentially, from now on, okay, everything about down conversion will be inside of this factor G naught. And well, you can see some interesting features of these factors. So for example, of course, it is proportional to the nonlinear susceptibility. It is proportional to the width of the material of the nonlinear dielectric, and then some other dependencies, but nothing really too interesting. So what's interesting, it's actually the physics that will come out of this Hamiltonian, and this is what we are going to try to do today. So the first thing that I have to tell you is that this Hamiltonian, even though it looks pretty innocent in the sense that it has only two modes and they are coupled in a not too complicated way, this Hamiltonian doesn't have an analytic solution, okay? In the sense that we cannot find the eigenvectors and eigenvalues of this Hamiltonian, so the spectrum of this Hamiltonian. However, we are going to make an approximation that it's a relatively good approximation for down conversion, under which we will be able to find everything analytically about the properties of the down converted field. And this is what we will start today with in lecture 10. So let me go to it. So this is what we will call the parametric approximation, okay? So under this parametric approximation, everything will be analytical. And then let me try to introduce this parametric approximation first. So let me come back to what down conversion is. Here we have it. So essentially, down conversion means that we have a very strong field. So the pump field, so the field that it's at frequency 2 omega 0, is a very strong field that acts just kind of an energy reservoir for the down converted mode to take, okay? So then one approximation that we can make is that actually this down converted field is a reservoir, which is a field, a classical field that acts just as a source of energy for the down converted field. And that's essentially the parametric approximation. So let me write it down carefully. So the parametric approximation refers to treating the pump So treat pump as a strong classical field source. So this is very similar to what we did for the light matter interaction when we had a single atom interacting with the electromagnetic field. And then we made the approximation that the electromagnetic field was classical and we got only beautiful Rabi oscillations, okay? So we saw that when actually the field is in a coherent state, that it's very large photon number, then that's actually a pretty good approximation. And we don't see collapses and revivals and so on within the time scale that we care about for the Rabi oscillations. So here we can do something similar, and we can now take this field that appears in the Hamiltonian, so E2, instead of taking it as a quantum field, we can take it as a classical field. And in particular, we can give this form to the electric field at that frequency. So let me just write it down. So this will be a classical field that depends on space and time then it has polarization in X, then we have the usual factor here, omega2 divided epsilon 0 and X L S. Then we have the mode profile. So this is the mode profile that we wrote. And now in a normal situation, so in a quantum situation here, we would have the annihilation and creation operators. But for a classical field, what we will have is just the oscillations in time. Okay. And then we will have an amplitude that is parametrized by the number of photons, or the square root of the number of photons at that frequency, but these are classical photons. So it's just a way of parameterizing the amplitude N2. Okay, so N2, it's assumed to be a very large number, so billions of photons, okay, such that this is a classical field. So in other words, and of course, we are choosing here a cosine of omega2t, but we could choose any type of oscillation. This is just the phase, the phase with which oscillations start. That depends on exactly which phase we give to the laser beam that we are using. But I just choose the cosine because it will simplify things. But the only important thing to remember is that this is equivalent, as I already mentioned, to assuming that the quantum mechanical state of your pump mode inside the cavity is a coherent state. In particular, in this case, it's this coherent state in here. Let me write it down. So it's a coherent state with photon number N2 oscillating at frequency omega2t. And then this classical field is nothing but the expectation value of the quantized component of the electromagnetic field in this coherent state. Okay, so just similarly to what we saw for the atomic case. And in particular, so as I say, this is a coherent state with N2 much larger than 1 photons. Okay, then when we make this approximation and we just do exactly the same kind of development as we did in here, so we just put here the classical field and then we proceed and so on, what we will obtain, it's nothing very surprising. It's just as if we would take the expectation value of this down conversion Hamiltonian in this coherent pump state. So in particular, let me write it down, and then we can discuss it. What we will get, it's a Hamiltonian that has this form. So it's a time-dependent Hamiltonian that has the free term for the down-converted field. And then it has the down conversion part, but the down conversion part, now it doesn't have the B mode because that's a classical mode. It's a classical field. And what we get is something slightly different. It's this thing here. So we get this with a new coupling constant that is nothing but the old coupling constant G0, so the down conversion rate, but we call it dressed, okay, dressed by the classical photon number. So this is usually called the dressed down conversion rate, okay? So just if you take a look at this Hamiltonian, you see that essentially we have the creation of two photons multiplied by a factor e to the minus I omega 2t. And if you come to the previous Hamiltonian, so to the full Hamiltonian, that's exactly the expectation value of B, okay, in this coherent state in here. So when you take the expectation value of B, you will just get this amplitude here that will give you the factor square root of N2 in front of G naught and the oscillating factor, okay? So now this Hamiltonian, we can finally treat analytically. And this is not a coincidence that we can treat this particular Hamiltonian analytically. This actually happens whenever we have a Hamiltonian that is quadratic in annihilation and creation operators. So any Hamiltonian that you are given that it's quadratic in annihilation and creation operators or in position and momentum operators, whatever you want, for as many modes as you want, that kind of Hamiltonian can be treated either analytically or at least semi-analytically. So maybe you need to diagonalize a matrix or things like this, but it can be in principle treated almost analytically. In our case, this is fully analytical, and I will show you how to treat it. And in particular, the first thing that you observe is that we have a time-dependent Hamiltonian, okay? Dealing with time-dependent Hamiltonians is always more complicated than with time-independent ones. So the first thing that we need to do is we have to move to a picture, okay, where the Hamiltonian becomes time-independent. This is very simple in this case because all the time dependence is just a rotation of the operators or a rotation in front of the operators A and A dagger or A and A dagger square. And therefore, just doing a very simple change of picture like this one. So let me write the change of picture. So we are doing a picture change defined as usual by a unitary transformation that is just defined by some kind of Hermitian operator HC. And in our case, HC will be the following. So in order to remove this oscillation at frequency omega 2, because we have here A square, what we need to do is we need to use as the Hamiltonian of the change of picture just one that it's at half the frequency that we want to remove. Okay, if we do this, then as I'm going to show in a second, so what we call the intermediate Hamiltonian or the Hamiltonian in the new picture takes, so I remind you that it always takes this form in here. So this is general for any transformation of this type. Okay, and in this particular case, because when you apply UC, so UC dagger to the operator A, this is just like free evolution. So it just gives the factor that we have already used in other occasions, which is it will start oscillating at the frequency that you are giving in here. So omega 2/2. So using this, that either you remember because we have used it already, or you just you can prove it with the Baker-Campbell-Hausdorff lemma. Then the Hamiltonian takes a very simple form. So this one that I am going to write. So we have kind of a free term, and then we have the down conversion term. However, what's interesting is that now this becomes time independent. So it's a Hamiltonian that is very similar to the previous one, but it's time independent. And it's also important that the definition of this delta that appears in there is the detuning between the down-converted frequency omega 0 and half of the pump frequency. Okay, so this is a detuning. So essentially, now this Hamiltonian here is what I am saying that can be treated perfectly analytical. So we can find eigenvectors, eigenvalues, the full spectrum of this Hamiltonian. And this is what we are going to focus on for the first part of this lecture. We are going to diagonalize this Hamiltonian and understand what it brings. Actually, it's interesting that I say we are going to find the spectrum, but one of the things that we are going to see from this Hamiltonian is that it's one of the first examples of something very general in bosonic systems that appears in many fields of physics, which is something that we call instability of the Hamiltonian, or in other words, that the Hamiltonian becomes non-diagonalizable. So it doesn't have a spectrum, it doesn't have well-defined eigenstates, stationary states. So this is something that we are going to study here, but for now, let me just start by trying to diagonalize it. So how can we diagonalize this Hamiltonian? This is actually pretty simple to do with something that is called Bogoliubov transformations, okay? So here we are going to see Bogoliubov transformation for this Hamiltonian, which is a single mode problem. It has only one mode, one annihilation and creation operators, one pair of annihilation and creation operators. But actually Bogoliubov theory is something that has its full power when we have many modes, okay? And then with many modes, we can use this Bogoliubov theory to understand analytically this kind of quadratic Hamiltonians. But for a single mode, let me just introduce Bogoliubov theory or the Bogoliubov transformation. So the Bogoliubov transformation for this single mode, it can be written in the language that we have been using in this course. It can be written in the following way. So when I say transformation, I mean that we take the original operator A and we apply some transformation, some unitary operation to it that will depend on a parameter R. And this defines a new operator C, okay? And for a single mode, this S, so this unitary, it's actually nothing but our well-known squeezing operator. So let me write it down. So where this set, it's some complex number that has an amplitude or a magnitude R and some phase theta. So I remind you that this operator, we worked with it at the beginning of the course, in particular in chapter 2. We worked with it a lot. And this is essentially what we call a squeezing transformation or a squeezing operator that creates this kind of squeezed states that we were discussing. And a Bogoliubov transformation for a single mode, okay, that's actually equivalent. So it's the same as a squeezing transformation. So let me just write it down. So this is for a single mode. Okay. So for more modes, you can imagine that you have a similar kind of transformation, but now mixing all the modes with themselves. So in particular, we saw in chapter 2 that this squeezing transformation applied on the annihilation operator, it gives you something of this type. So it gives you a linear combination of the annihilation operator and the creation operator. Okay, with where R is the squeezing parameter. And in our case, this R, we will choose it in a second, okay? So for now, we are just making this transformation and seeing what happens to the Hamiltonian. So this is this is the generic type of Bogoliubov transformation in which you define a new set of modes, okay, with annihilation operators that are a linear combination of the all annihilation and creation operators, okay? And as long as the factors that are in front of the A operators and the A dagger operators satisfy that the square of one minus the square of the other is equal to 1, then the commutation relations are left invariant. So this C defines a new annihilation operator. And of course, you can always, because we will use it now, you can always invert this relation and you can write the original annihilation operator in terms of the Bogoliubov annihilation operator in this way, cos R plus C dagger sinh R, okay? So let me make this transformation in the Hamiltonian and let's see what we get. Or more than making this transformation, what I will do is just, I will write the Hamiltonian in terms of the new operators, in terms of the Bogoliubov operator. So in terms of the C operator, then the Hamiltonian reads as follows. So the Hamiltonian takes the following form. It has an independent term that depends on R. Then we have a term h bar omega that depends on R as well, and has, let's say, the free evolution of the Bogoliubov operator or the Bogoliubov mode. And then we have kind of a down conversion term with rate kappa of R as well, that it's also given in terms of the Bogoliubov operator. And of course, the Bogoliubov operator satisfies canonical commutation relations. Okay, so then I will give you in a second exactly what is omega of R, kappa of R, and E0 of R. But the first thing that you might tell me is, did we gain something from this transformation? Because the form of this Hamiltonian is exactly the form that we had already. Okay. However, what's important is that now you see that we have a parameter R that we can choose. Okay, it's our choice. And we can therefore use this freedom to simplify the Hamiltonian, and in particular, we will try to remove this term in here, because then we are left with a very simple Hamiltonian, which is just the free evolution of a harmonic oscillator, just a Bogoliubov harmonic oscillator, not the original one. So let me see if this is possible. So in particular, this Hamiltonian, the parameters that I defined in here are the following. So if you just introduce this transformation into the Hamiltonian, you can write down things in this simple way. So the term in front of C dagger C can be written as the delta times the not the cosine, but the hyperbolic cosine of 2R minus G in the hyperbolic sine of 2R. Then this kappa, it's kind of the opposite combination or the complementary combination. So the cos of 2R multiplied by G minus the sine of 2R multiplied by delta. And this energy offset, it's very simple. It's just h bar over 2 times the omega that I just defined minus delta, okay? So just as I say, this you find just by making this transformation or inserting this transformation into this Hamiltonian. If you do that, that's what you get. Then this immediately shows us that if we choose R such that this expression is equal to 0, okay, then we are left with a very simple Hamiltonian. So in particular, what I am saying is that if we choose R such that the hyperbolic tangent of 2R it's equal to G divided by delta, okay, then this automatically implies that the kappa term is 0, and you can also check, so you have it in the notes or you can try by yourself, but you can check very easily that the omega takes this simple form. Okay, so it's essentially the square root of delta square minus G square, and then it has a sign. It has a sign that can be positive or negative because the detuning can be positive or negative. And then with this, the Hamiltonian takes a super simple form that we are very familiar with, which is just an energy offset plus h bar omega c dagger c. So what is this? This is just a free harmonic oscillator. Okay, and we know very well what is the spectrum of a free harmonic oscillator. So in particular, so the spectrum takes a very simple uniform expression, which we have already seen. So remember, because C is just an annihilation operator, C dagger C is a number operator, just of a new mode called Bogoliubov mode. And therefore, we can define the eigenstates of this operator, and in particular, the spectrum will take this simple form that we have already seen. However, now there is something very interesting. So this spectrum, so if omega is positive, is just what we have seen before. So in particular, it starts at energy E0. It starts at energy E0, and then we get this kind of stair, this ladder, in which we have here a uniform spacing h bar omega, okay? And this means that, so this thing in here, this happens for delta larger than 0 because omega is positive, okay? And then we have a lower bounded spectrum, and that's the key point in here. So we have a lower bounded spectrum and just a uniform spectrum with a gap h bar omega. However, what's interesting is that when the detuning is negative, so if we are in the opposite region, so if we are here, so we get a spectrum that it's also uniform, but it's actually going in the downwards direction. So now we don't have a lower bounded spectrum, we have an upper bounded. An upper bounded spectrum. And I'm pretty sure that you are not very familiar with upper bounded spectra because this cannot happen in a normal Hamiltonian. This is only possible, okay, this thing in here is only possible for systems that are out of equilibrium. Okay, And when I say out of equilibrium, what I mean is that you have your system that in our case is just the down-converted mode, which let's say in the absence of anything is just a harmonic oscillator that is very lower bounded and very happy staying there. But then you apply something that provides energy and that brings it out of equilibrium. This could be an interaction, but then an interaction with a system like the pump mode. But if you take into account everything, the pump mode and your initial system, you just get a Hamiltonian that describes an equilibrium system. But if you forget about one of them and you use one of them just as a source of energy, this essentially brings out of equilibrium the other mode, and in particular makes the Hamiltonian time dependent, okay? So when you are analyzing a time-dependent Hamiltonian in a picture where it is time-independent, you can have this kind of physics in which your Hamiltonian looks upper bounded instead of lower bounded, okay? But again, this is something very special of the kind of situation that we are studying here. So this is for the spectrum. Now, how about the eigenstates? So as I said, the eigenstates of this Hamiltonian are nothing but the eigenstates of the number operator C dagger C. So this operator, just based on the properties of the annihilation and creation operators, we can define some kind of Fock basis that will be a basis of eigenstates of this C dagger C operator. And I will call them N sub C. So we know that these are the Fock states associated to the Bogoliubov mode, not to the original mode. And what I am going to show you now is that actually these eigenstates, when you write them in terms of the original mode, take this very interesting shape. Okay. So they take this shape. So the Fock state of the Bogoliubov mode, it's equal to the Fock state of the original mode, which is a Fock state of our electromagnetic field, because A is the operator that defines the electromagnetic field, but squeezed. Okay? So we are applying a squeezing transformation. And so this means that the eigenstates of this Hamiltonian are squeezed Fock states of the original operator. Okay. So this I am going to prove now, but you see that this is actually very interesting because it's already telling us that this Hamiltonian has some relation to squeezed states, okay? So the eigenstates of this Hamiltonian are no longer the bare Fock states of the cavity, but the squeezed version of these ones. So let me just prove this to you because it's very simple and very instructive. So the first thing that I can do, so let me start by doing this for the vacuum state first. So the vacuum state of the C operator is defined as the state that is annihilated by this operator, right? But now I can just use the definition of C. I remind you that C is nothing but, you see here, just S dagger A S. And therefore, what I get in here is S dagger of R, A S of R acting on the vacuum state of the Bogoliubov modes equal to 0. But look, we have in here that A acting on this state here is equal to 0. Okay. So you can remove this S dagger. For example, you can multiply the whole expression by S on the left. Then you remove this one, And then what you get is that A acting on this state, it's equal to 0. But that means that this state in here is by definition the vacuum state of the A operator, okay? Because that's the definition of the vacuum state of the A operator, is the state that it's annihilated by it. And therefore, this automatically proves, if you just invert this relation, that the ground state or the vacuum state of the C operator, of the Bogoliubov operator, is just the proportional to the vacuum state of the A operator, but now you will have the inverse of S of R. And S of R is a unitary, so then you will have S dagger. But at the same time, if you just look at the form of S, just changing set by minus set is the same as making the dagger. So this is something that we already saw. So then this is just S dagger of R or S of minus R. It is the same. So then this proves the expression above for the vacuum state. Now we can, using this, we can show that this is the case for any number state, for any Fock state, in the following way. It's very simple. So what is the definition of a Fock state N? So this means that we have to apply the C dagger operator, so the creation operator N times onto the vacuum, and just divide by square root of N factorial for normalization. And then if we again expand both C and the vacuum state in terms of the corresponding things in the A basis, in the original basis, we have this expression here. So C, it's nothing but S dagger, as we have seen already, A, so then we get here A dagger to the N, and then S. And the vacuum state, it's nothing but S of minus R, and then the vacuum state of A. But what do we have in here? This thing in here is just the identity, because we have S and the inverse of S. So therefore, we are left with something very simple, because we have A dagger to the N acting on the vacuum of A, and this is precisely with the normalization factor is the Fock state N, but now of the basis A. And then we are left with one S dagger of R operator, and as I mentioned, this is just the same as S of minus R, okay? So this proves that this expression is true for all Fock states. So in other words, from here, apart from having been able to diagonalize the Hamiltonian, okay, and have the spectrum and eigenstates, and now we can calculate anything we want, and we will do it. Apart from that, we already see something that is conceptually very profound, which is that down conversion generates squeezing in the field. Of course, in the down converted field. So this is exactly what is used in order to generate squeezing in experiments, okay? So you have a second order nonlinear material, and then you pump it very hard with a classical field, and you get a down converted field that will have these squeezing properties. And as some of you have been asking actually offline, from this kind of squeezed states, you can also generate entangled states, and you can generate many states that are very important for quantum information protocols, okay? So this is why these kind of states are very, very important. So before we make a break, let me just mention one thing. This is kind of a very nice theory. However, I omitted a big thing. So there is a big, big elephant in the room. So, which is this expression here. It's only possible provided that delta is larger than the coupling. So let me make it clear. So you see here that this is a hyperbolic tangent. The hyperbolic tangent is always bounded by -1 and 1 because it's the sine divided the cosine. The cosine is always larger than the sine, I mean the hyperbolic ones. And therefore, this expression in here, it's only possible to satisfy when this right-hand side, it's between -1 and 1, which means that delta needs to be larger in absolute value than G. So if this doesn't happen, all this theory that we developed in here, it's actually not true. I mean, we cannot define an R that satisfies that kappa is equal to 0, okay? So then this theory applies only to the case in which the detuning is larger than the down conversion rate. And if this is not the case, we have to do something else. And that's what we are going to do right now. So if you want, we can make a break and regroup at 2, so in about 10 minutes, 12 minutes. And then we will continue with the analytical treatment of this Hamiltonian, okay? So see you in 10 minutes. Okay, so welcome back. So now the question is, what happens to this Hamiltonian when we are in the region in which the down conversion rate is larger than the detuning? So that's what I want to discuss now. And so let me write it here. We are going to work now in the regime in which the detuning is smaller than the down conversion rate. So as I said, if we look at the form of the Hamiltonian, in this case, we cannot choose R such that kappa is equal to 0, okay? But we see that because omega is a complementary combination, now what we can choose, or the best we can do to simplify the Hamiltonian, is choosing omega equals 0. So in particular, now the best simplification of the Hamiltonian happens when we choose the opposite combination. So the hyperbolic tangent of 2R, it's equal to delta divided by G instead of G divided by delta. And then in this situation, delta becomes 0, sorry. What we call omega becomes 0. Omega is the factor in front of C dagger C. And then kappa becomes just the square root of G squared minus delta squared. Okay, then in this case, the Hamiltonian gets simplified to the following Hamiltonian. So we still have the energy offset is 0, and then we get h bar kappa over 2 and C dagger squared plus C squared. Now, this is the best we can do to simplify the Hamiltonian. And now I can ask you, okay, can we diagonalize this Hamiltonian? Can we find the spectrum of this Hamiltonian? Well, what I am going to convince you of now is that actually this Hamiltonian doesn't have a spectrum. It cannot be diagonalized. And I show you why very, very easily. Later, we will see it even better with one example. But right now, you can just understand this from the following simple argument. So this term in here, so including the minus sign. So if I rewrite it in terms of position and momentum of the operators C of the Bogoliubov mode, so in particular, if we take the annihilation operator C and we write it as 1/2 of X plus IP, okay? Remember X and P are quadratures, their commutator is equal to 2I. Then if we just use this definition of positional momentum, then we get this Hamiltonian. So this expression becomes h bar kappa over 4, and then p squared minus x squared. And what is this? So this thing here, let me write it down, is just an inverted parabolic potential. Or in other words, we have a particle which has some kinetic energy, p squared, but the potential is not just a parabola x squared, it's a parabola with a minus sign, it's minus x squared. So now, I don't know if you have studied this, but you can imagine that if you have a parabolic, an inverted parabolic potential, which means that the potential energy goes to minus infinity when x goes to infinity, this problem cannot have possibly stationary states, because no matter where you put the particle, what the particle will try to do is go to infinity, because this is where the energy becomes smaller and smaller and smaller. It becomes more and more negative. So what you will get is that you will not be able to build stationary eigenstates of the Hamiltonian, so states that are not evolving or are evolving trivially just by a phase. And therefore, this Hamiltonian in here is an example of a Hamiltonian that is non-diagonalizable. Okay, we call it unstable. Okay, so whenever you hear something along the lines of bosonic instability or simply an instability, it always means something of this type. It always means that you are moving around a potential that is not bounded. Okay, it's not bounded, and not only that, but it goes to minus infinity as you move outside of the origin, and then this tells you that you will not have stationary eigenstates. Okay, so this, as I say, we are going to analyze an example shortly, and you will see a little bit more how this appears in a dynamic setting. So how, if we start from a natural state of the harmonic oscillator, it will just grow and grow and grow and grow towards an infinite number of excitations. But this is all I want to say about this Hamiltonian at this moment, okay? Then you can ask me what happens when we are, because we have checked what happens when delta is larger than G, when delta is smaller than G, but what happens exactly at the boundary? So what happens when delta is exactly equal to G? So when the down conversion rate and the detuning are kind of equilibrated. So the first thing that you can see is that, well, if delta is equal to G, then either from this expression here that you see that this is equal to 1, or from the previous one is the same, so this is equal to 1 as well. Then if the hyperbolic tangent is equal to 1, this means that R goes to infinity. So the hyperbolic tangent, which is the sine divided the cosine, that's equal to 1 only when R goes to infinity. So then the first thing that you see is that exactly at that point, we have kind of an unphysical situation, because we have a squeezing that goes to infinity. So let me write it. So this is infinite squeezing. Okay, and as we have discussed, infinite squeezing is not physical because it requires an infinite energy. And of course, the energy we are taking is from the pump field, which is a very strong field, but it doesn't have infinite energy. And moreover, if we remove too much energy from it, we cannot assume that it's just a fixed state. At some point, we will have to describe the dynamics of the pump because we are removing energy and it will change. But in any case, just imagine that we are in this limit of delta equal to G, and let's understand what our Hamiltonian gives us. And this we can do in a very simple way. So for this specific situation, let me write the Hamiltonian in terms of position and momentum, but position and momentum of the original operator. So x plus IP, and these are the position and momentum quadratures that we have defined for the modes that we work with usually, and in particular for the mode that describes the field. Then, if you introduce this into the Hamiltonian, what you will get is the following. So the Hamiltonian is easily written in the following way. So let me just write it down, and then we can discuss it. So if you just make this expansion for the A operators into this Hamiltonian, so the original Hamiltonian in here, but you take delta equal to G except for the sign of delta can be positive or negative, then you just rewrite it very easily. So it's automatic to rewrite it in this form, okay? And this means that depending on the sign of delta, so the Hamiltonian will be proportional to the momentum square. So this is for delta positive, or proportional to the position square. This is for delta negative. Okay? So this is very interesting because this is telling you that in the limit in which delta is equal to G, the reason why R goes to infinity, so why the squeezing goes to infinity, is because now the Hamiltonian is actually that of a free particle. Okay? So this Hamiltonian is just exactly the Hamiltonian of a free particle. Okay? And in particular, because it's the Hamiltonian of a free particle, the eigenstates of the Hamiltonian will be either the momentum eigenstates or the position eigenstates, depending whether delta is positive or negative, okay? With energies that will be all the real line, sorry, not the real line, but it will be a continuous spectrum that will have all the positive values for delta positive, and when delta is negative, it has all the negative values because we have a minus sign in here, okay? So in other words, the spectrum becomes continuous. So we have a continuous spectrum, and we have, as eigenstates, we have the momentum eigenstates for delta positive and the position eigenstates for delta negative. So then we have a very interesting situation in which what you see is the following summary. So let me just summarize. I already made the table. You don't need to copy it because you will have it right after the lecture. So let me just explain you. So if we start with very large delta, okay? Delta much larger than G. Then if you go to the Hamiltonian, to the original Hamiltonian, you see that when G is much smaller than delta and you neglect all this term, okay? Then the Hamiltonian is just a dagger A, which is just that of a free harmonic oscillator, lower bounded with a uniform discrete spectrum, okay? So this is what we get. When delta is larger than G, we have a discrete lower bounded spectrum, and we have as eigenstates, we have seen that we have Fock states, but not just any Fock states, but squeezed Fock states, okay? Now, when you are exactly at G, what happens is that this discrete spectrum, the gap in between the in the spectrum, it becomes smaller and smaller and smaller as delta becomes closer to G, because I remind you that this omega here is delta square minus G square, okay? And then when delta is equal to G, omega becomes 0, and all the steps, let's say, all the energies of the spectrum kind of try to collapse into one, and that sets the limit in which actually what happens is that the spectrum becomes continuous, still lower bounded, and now the eigenstates are not just momentum squeezed, but they are perfectly squeezed, which means that they are momentum eigenstates, okay? So that's the spectrum for delta equal to G. Now, when you are between G and minus G, so when the detuning is between G and minus G, then the Hamiltonian is non-diagonalizable. There are no stationary eigenstates, which we call unstable. And this is also easy to remember because, for example, well, when the point in between G and minus G is 0. So if you go to the original Hamiltonian and you put delta equal to 0, what you get is just a squared plus a dagger squared. We have just seen that that's equivalent to an inverted parabolic potential, and therefore you know that you don't have bound states, you don't have eigenstates of the Hamiltonian. So that's just kind of for you to remember. And then when we go below minus G, so when the detuning becomes larger than G, but with negative sign, then what happens is that, well, exactly at G, we again get a continuous upper bounded spectrum. So it's a continuous spectrum, but now it's upper bounded. And the eigenstates are no longer momentum eigenstates, but position eigenstates, okay? And then if you go below, you again get a discrete spectrum, but now it's upper bounded instead of lower bounded. And the eigenstates of the Hamiltonian are Fock states, but position squeezed, okay? So this thing in here summarizes the whole physics of this down conversion Hamiltonian under the parametric approximation, okay? And what I want to do now, it's I want to use this this kind of analytic treatment that we have done of the Hamiltonian to understand better this instability, this unstable behavior in practical terms. So for example, how would you try to identify whether you are in the stable or unstable phase? One simple way would be to measure the number of photons inside the cavity. So if you check the number of photons inside the cavity, when you are in the stable region, so when the detuning is larger than the down conversion rate, you should have a situation in which the number of excitation doesn't diverge to infinity because you have bound states and so on. And I will show you that this is the case. On the other hand, if you are in the unstable region, what we will see is that starting from the ground state of the cavity, what we will have is that it starts increasing the number of excitations exponentially, okay? So this is what I want to do now as an example of use of this physics. Let me try to understand in practical terms how to evaluate the photon number, the evolution of the photon number. So let's see the instability in practical terms. And for this, what we are doing is the following. We assume that at time 0, the state of the system is just the vacuum of the cavity, okay? And then we let the system evolve. So now we ask ourselves, what will be for some time t, what will be the expectation value of the photon number? So this is what we will call just the average of n as a function of time And I remind you that this is just the number operator that we called n. So this is the question. So given the Hamiltonian, let's try to evaluate how the photon number evolves. So the first thing to note is the following. So we are working in an intermediate picture in which we are rotating at the frequency half the frequency of the pump. And in this picture, of course, you can always write also the expectation value as the state in this picture and the operator in this picture. Okay? Now I remind you that what I mean by this is the operator in this picture is nothing but applying the transformation operator onto the operator that you are considering. And in this case, it's very nice that the operator doesn't change. Why? You see it right away. Because if we go to the transformation, you see that the operator A transforms in this picture as A and then some phase. Okay. A dagger transforms with the opposite phase, with the plus. Then if you take the product A dagger A, these phases go away and you are left just with A dagger A. Okay, you are left with what you had already. So in other words, this is what we get. We get that in the intermediate picture or rotating picture that we are using, the operator n takes exactly the same form, A dagger A, nothing changes. On the other hand, of course, the evolution of the state in this intermediate picture is given by the time evolution operator in this intermediate picture, and this is psi of 0. And the time evolution operator in this intermediate picture is nothing but the exponential of h in this picture divided IH bar multiplied by time, okay? So then using these two definitions, so just the transformation of the operator to our picture and the transformation of the evolution of the state to our picture, then we see that actually the form that we have for this average photon number, it's just the following. So let me write it down. So we have the state at time 0, then the evolution of that state. Oops. In the picture we are working with, then the operator n, and then the same for the ket instead of the bra. But this is very nice because, as you see, this part in here and this part in here are Hermitian conjugates. Okay, so this is a ket and this is the corresponding bra. So then this expression here is nothing but the norm of this ket, the norm square of this ket. Okay, so all we need to do is evaluating this ket in here and take the norm square, and we are done. Okay, this gives us the photon number. This is a very useful trick, and in particular, it will be even simpler to, instead of considering just that particular ket, of course, we can always add here a unitary transformation. And then this is nice because, as you will see, or as you see already, this is just the transformation of the A operator under the action of the unitary evolution operator. And this is very trivial to find, as I'm going to show you, in any region that we work in. So In particular, let me just, so you see how this is done, let me consider first the situation in which we are in what we call the stable region, or the region where the Hamiltonian can be diagonalized. In this case, the time evolution operator in the intermediate picture is given by just the term that has the energy offset, and then the Hamiltonian in this case. So let me just remind you quickly. The Hamiltonian in this situation can be written as h bar omega c dagger c, and therefore the time evolution operator is nothing but minus I omega t c dagger c. Okay. This is a very simple Hamiltonian because it's just free evolution of the Bogoliubov mode. And we know how to deal with this very easily. In particular, we have that n of t will be equal to the absolute value, so the norm square of this transformation, acting on the vacuum state of A. And now, how do we deal with this? So it's very easy. We know very simple how this transformation acts on the operator C, okay? So I just show you again that if you have the exponential, so for example, for an operator A, if you have the exponential of A dagger A, it's just a phase, right? So the same happens for C. If you have here C and you put C dagger C, then you get a phase. Therefore, what we can do is we simply take the transformation of A into C, then we apply the unitary transformation to C and C dagger, and we come back to A using the opposite. So this is how you proceed to do the calculation simple. And let me write it down. This is what we have. So first of all, we take A and we write it in terms of C. How do we do that? So we have this expression here that we have just seen. Okay. Now we apply this unitary transformation onto C and C dagger. And this gives us e to the minus I omega t and e to the plus I omega t. So all this operator is just equal to this operator in here. And finally, now we have this operator acting on the vacuum state of A. So what happens? That now the component of this operator that has A will annihilate it and will not contribute. So now we need only the contribution of this operator to A dagger and the contribution of this operator to A dagger. But I remind you, that this operator, the contribution, or let me do first this one, the contribution that goes with A dagger is nothing but cos R and A dagger. And in the case of C, it's just minus A dagger and sine, hyperbolic sine of R, okay? Let me show you once again, just so I'm sure you are not lost. C is equal to minus A dagger hyperbolic sine. Therefore, C dagger will be equal to A dagger cosine. This is exactly what I am writing here. And therefore, the final expression will be this one in here. So we will have the hyperbolic sine, the hyperbolic cosine, and then an exponential of plus I omega t minus I omega t. And then we have A dagger acting on the vacuum state of A. And we want the norm of this. So this thing in here is just the Fock state 1. This thing in here is just 2 times I sine of omega t. And this thing in here, therefore, together with the 2, or if you want, this is just 2 times the hyperbolic sine of r, sorry, of 2r. And when you put everything together, what do we get? So let me make some space because I want to do a plot. So let me make this slightly smaller. I hope you can see it well. So the final expression, it's just the hyperbolic sine square of 2r times the normal trigonometric sine square of omega t. Okay, and we can plot this. So it's always a good idea to make a plot, and the plot looks like this. So I will plot as a function of omega t, the absolute value of omega. You see that this expression, it doesn't matter what is the sign of delta. So the sign of delta appears only as a sign in omega, but this is a sine square. So then it doesn't depend on the sign of omega. We can even put here the absolute value if we want to make it clear. And then we are plotting here the number of photons. And this is just a function that looks like this. Well, you know what I mean. It's not very carefully crafted, but you understand. So now the point is that we will have a maximum whenever we are at, so essentially pi over 2, and then in here we go to 0 again at pi and so on. And that maximum, it's equal to the hyperbolic sine square of 2r, that if you go to the definition of r, this is just the following factor. And without square root. Okay, so let's see what this is telling us. What we see here is that we have oscillations, okay, bounded oscillations that go between 0 at time 0 and a maximum at times pi over 2, 3 pi over 2, etc. And what's important is that these oscillations are bounded. So in particular, they are proportional. The maximum is proportional to g squared, okay? And therefore, when the coupling is equal to 0, we have 0 amplitude of oscillation. So we are in the vacuum state all the time, 0 excitations, 0 photons, which is what we expect because we don't have down conversion. And then if we have some down conversion rate, then we get periodically to some maximum. And of course, at this point in here, we have maximally, or let's say this is the best squeezing that we can get for that coupling G, okay? So this is a way of generating a squeezed state at each pi over 2. Okay, but the important thing, as I said, is that here the oscillations, or the number of excitation is bounded, okay? It's finite all the time. Now, let's see what happens in the opposite situation, so when delta is smaller than G. So as I already told you intuitively, we expect that the number of excitations will grow exponentially because the particle just wants to go quickly to minus or plus infinity, okay? And that's exactly what we are going to show now. So analytically, and this is the following. So first of all, the time evolution operator in this regime, it can be written as the energy offset as usual, and then we have an exponential, and let me remind you quickly, the Hamiltonian in this region is equal to this thing here, okay? So C dagger square plus C square, which means that the time evolution operator is equal to I kappa T over 2 C dagger square, plus C square, okay? Now, what's interesting is that this thing in here, so the time evolution operator itself is nothing but a squeezing transformation for mode C. So let me write here a sub C with squeezing amplitude minus I kappa T. So in other words, this is a squeezing transformation on the Bogoliubov mode C with squeezing parameter set equals to kappa T and e to the I pi over 2, actually minus I pi over 2. And what's important is to notice that this squeezing grows with time, okay? So the time evolution on itself is a squeezing transformation, but it's not a stationary squeezing transformation, it's a squeezing transformation that increases with a squeezing that increases in time, okay? And of course, we know that the number of photons increases exponentially in the squeezing parameter, okay? And therefore, if the squeezing parameter is linear in time, this means that the number of photons will increase exponentially in time. And this is what we are going to show. So let me show you again analytically n of t. Now this is equal to the norm square of this squeezing transformation on A so this is acting on the vacuum state, which is the initial state. And now, again, we have to do the same kind of trick as before. A is equal to what? As we have written already, this is the hyperbolic cosine of RC plus C dagger hyperbolic sine. And now we have to transform this with the squeezing transformation on C. But we know that the squeezing transformation acting on C, that's equal to, again, this comes from the chapter 2. This is just equal to the squeezing parameter. So C, hyperbolic cosine of the squeezing parameter, plus a phase. And in this case, the phase is just because we have a phase pi over 2. We get here a phase pi over 2. And then C dagger and the hyperbolic sine of the squeezing parameter. And now we have to do the same as we did before. This C is just, in terms of A dagger, is just the minus sign and we have A dagger, and this C dagger is just the cosine A dagger. So when we put all these things together, the final expression that we get, it's also very simple, and it looks like this. This is the cosh of 2r, the sine, the hyperbolic sine of kappa t, and then again we get just A dagger acting on the vacuum state. So then the final expression is just the cosh square of 2r times the sinh square of kappa t. And you see that now it's very different because before we had a trigonometric sign of the time. Now we have a hyperbolic sign of time. And the hyperbolic sign is not a periodic function. This is a function that makes the photon number look like this. So if we make the plot of photon number against kappa t, we will just have something that increases, and it increases exponentially as 2 kappa t. Okay, because the sign, the hyperbolic sign square, increases for time larger than kappa as e to the 2 kappa times t. So in other words, we have an exponential explosion of the photon number, which gives the name, or makes kind of intuitive the name instability for the Hamiltonian in this region. Okay, so I hope that this example shows you how with bosonic Hamiltonians you have to be very careful, and you can have regions of these Hamiltonians in which, if the potentials are not bounded enough, or are too unbounded, let's say, or go too fast to minus infinity when x increases, then you have to be careful because you can have this kind of exponential explosion of excitations. Of course, in a real physical system, whenever this happens, it's because you are not taking the real physical Hamiltonian, because an exponential, so to sustain an exponential increase of excitations for infinite time, you need infinite energy. And this is not available. And therefore, this means that after a while, after you have consumed enough energy, your model cannot be possibly described by the Hamiltonian that you were using, okay? Because you need to start describing either other processes that are in your system, or the energy reservoir that you are taking energy from. You have to start describing the dynamics of that system as well, such that it doesn't give you an infinite energy all the time, okay? So these are things that you have to take into account, but the only thing that I wanted to kind of make sure that you understand in this chapter is that down conversion, it's a way of providing squeezing, okay? And you see that squeezing appears in many forms related to down conversion, to the down conversion Hamiltonian. Okay, so I think that now we are going to change to a new chapter. So this is a very good point to make questions about this thing that we have just seen, if you have any. Otherwise, as usual, you can ask me offline. And if not, what I suggest is that we make a final break now, And then we start with the new chapter about open systems in 10 minutes. So let me maybe stop the recording. Okay, so welcome back, and welcome to a completely new chapter. And as I said at the beginning of this lecture, this is probably one of the most distinctive and most important chapters of the quantum optics course, because we are going to study quantum optics, but not in closed systems, but in open systems. And I will start by explaining what I mean by open systems and what I mean by a description of an open system, first in general terms. And then I will introduce the subject through one very simple example and very natural example, which is an open optical cavity. So this is a cavity that has a partially transmitting mirror, and therefore we can have light going in and light going out. And as you can imagine, this is actually what happens in a real system. In a real system, we need, so in a real optical cavity, in a real quantum optics experiment, we always need to be able to send light inside the cavity. For example, you have seen in the previous chapter that to create squeezed states, we need to pump the nonlinear crystal with a laser at frequency 2 omega 0, and that we do with an external laser coming inside the cavity. And also we want to use and observe the light that is generated inside the cavity, and for that light has to come out of the cavity. So one of the mirrors, at least one of the mirrors, need to have a bit of transmissivity so we can kind of monitor what's happening inside and use the light that, the squeezed light, for example, that is generated by the device, we can use it for experiments like for the interferometer of gravitational wave detection of LIGO, or any other kind of quantum information protocol that we need the light for, and whatever. So then let me first introduce what's an open system generically. So actually, let me tell you that what we have done so far is something like this. So we have taken a system that is described, or we have a system that we have assumed that it's perfectly described, of course, by a Hilbert space, but the dynamics of the system, it's perfectly described by a Hamiltonian H, okay? And we have assumed that that's all we have. We have a system with a Hilbert space that is simple and some kind of dynamics induced by a Hamiltonian that can be also relatively simple, like interaction of an atom with an optical mode or with a nonlinear dielectric and so on. But what we are going to study here is a different situation in which what we have is more similar to this. So our system is not closed, it's open. And by this, what I mean is the following, is that our system, that is the system that we are caring about, that we are doing the experiment with and whatever, it's not completely isolated, but it's actually part or interacting with a bigger system that we will call an environment. Okay, and maybe the combination of the system and the environment, okay, it's a closed system on itself. So that's why I write here a closed boundary. So this boundary here, it's really closed. So there is nothing from outside or anything like that. But the system that we care about, actually, it exchanges energy and in general, other types of information with this environment, okay? So there is an exchange of energy and information, and therefore, our system is no longer a closed system described by a Hamiltonian, the dynamics of which is described by a Hamiltonian, but because it is exchanging energy and information dynamically with the environment. For example, you can start with a pure state of the system, but end up with a mixed state, because we have seen that whenever we have our system sharing information with another subsystem, then you are left in general with a mixed state. So we need some kind of dynamics that are capable of generating these mixed states starting from pure states. Because as we have described before, only Hamiltonian dynamics doesn't change the fact that you are with a given value of the von Neumann entropy or the mixedness. So we will need something more. And in particular, the idea is the following. The idea is that the whole system plus environment, they are actually described by a Hamiltonian system, so by a Hamiltonian dynamics, okay? But we care only about what happens to the system. So what we are going to do, and this is what we are going to do in this part of the course, so this is going to be a relatively long chapter like the second one, in which we are going to study how to find dynamics, so dynamical equations for the reduced system. Okay, so we have the full universe that we will call. So maybe the combination of system and environment is the whole universe. And we care only about the reduced state of the system. How does that evolve? So what we are going to see here is that there are two descriptions that are equivalent, but lead to very different ways of proceeding in practical terms. One is called the Heisenberg picture. Sorry, so one is in the Heisenberg picture. And the evolution equations that you find in here are called quantum Langevin equations. Okay, so we will see that you can actually still describe the evolution of your system with a dynamical equation only for the system without degrees of freedom of the environment, but you have to modify Heisenberg equations of motion with something that we will call quantum Langevin equation. Or, of course, we can use the Schrödinger picture. And in the Schrödinger picture, we will see that the von Neumann equation or the Schrödinger equation needs to be modified as well into something that we will call master equation. Actually, this master equation description is something that is it's the most useful. So I use them in my research all the time, much more than quantum Langevin equations. But the quantum Langevin equations are actually very important for many reasons, in particular because working in the Heisenberg picture, we can also understand once you have the dynamics of the system, okay, you can understand how these dynamics are affected by the action of the environment. So environment action, but also you can see the reaction of the environment. So you can imagine that you have your cavity, you create an action from the environment into the cavity, you do something inside the cavity, like generating a squeezed state or whatever, and now that state has to go outside of the cavity through the partially transmitting mirror. And this reaction on the environment, so this field that comes out of the cavity, that's what we are going to observe in the laboratory. And that is very easy to describe in the Heisenberg picture through something that we will start in here and finish in the next chapter, which is called input-output theory. And you see that this is a very descriptive name because it's telling you how the things that you input into the system through the environment, how they come outside again, and then you observe them. So it's kind of an action-reaction theory. So, so before I start actually with the example and I show you exactly how to build quantum Langevin equations and how to build master equations and what type of dynamics they lead to, let me mention that this kind of tools, so these tools of system and environments, they are used in basically all the fields of physics that requires quantum mechanics and requires dealing with real physical systems. Because as you can imagine, it's almost impossible to isolate perfectly a system in the laboratory. That happens only in a few labs in the world, and only because they work very hard to observe some Hamiltonian dynamics on purpose. But in general, you always need to have this kind of description in which you have an environment that you are not monitoring, that you are not caring about, and you don't have control over it, and it's interacting with your system. And in particular, I have many friends working in other fields like condensed matter or electronic transport, heat transport, even high energy physics that need to use this kind of master equations in particular all the time, okay? So this is something that you are going to learn in quantum optics because it's the most characteristic thing of quantum optics, but that you will really be using if you continue doing quantum physics in other fields. So, or at least you can continue using it depending on the exact thing that you are working on. So I hope that this is enough motivation to kind of want you to understand a bit better what are quantum Langevin equations and what are master equations. So then let me start with the simplest example that we are going to study, which is an open optical cavity. And in particular, let me start introducing the model that we are going to use for an optical open optical cavity. So this means I have to define what is the system, and I have to define what is the environment, and I have to define what is the interaction between the system and the environment, okay? So that will be the basic model of the whole universe, we will call it. So let me then start with this, and I start letting you know the following. So first of all, so I hope you can see this. So the model that we are going to use for an open cavity is the following. So we have already studied a cavity in which we have a perfectly reflecting mirror and another perfectly reflecting mirror at position L. So what we will do now is just something very natural, which is that we will assume that this mirror at position L is not perfectly reflecting. So it allows a bit of transmission, okay, of light. And we will model what's happening outside the cavity. So outside the cavity, we have free space. Okay, you can imagine you have just two mirrors, and to the right of this mirror, we don't have anything. So it's just free space. It's just the electromagnetic field in free space. But in order to use the description that we have already considered, we can make a model in which we assume that outside of the cavity, we have another mirror located at distance L external with respect to the mirror L. And then this cavity is the external cavity that shares the partially transmitting mirror with the main cavity that we are interested on, okay? And of course, what we will do is that at some point, we will take, so this external field, this external space, it will be a cavity, but eventually we will take a cavity with infinite length. okay? And this is, of course, a very nice model because it really models what we want. So we will have, at the end of the process, we will have our cavity interacting with the electromagnetic field outside, which is essentially in free space, because you have a cavity with the mirror at infinity. Now, in order to make things actually simpler, but simpler in the sense of notation, we will consider just one mode of the cavity, okay? So we will start assuming that the cavity is empty. So it's an empty cavity, so it doesn't have anything. And we will consider just a single mode. Okay? Which will have a resonance frequency that we will call omega c, and annihilation and creation operators that satisfy canonical commutation relations, and we will call them A and A dagger. Okay? So essentially, we will now be interested, so our system is just one mode of the cavity of frequency omega c. In the environment, it's all the external modes of free space that will be coupled to this mode through the partially transmitting mirror, okay? So the first thing that I want to do, so the thing I will do in here is giving you how do we describe the external field, the quantized external field in this space that is just free space. So let me just start with this. So the first thing to note is, well, of course, let me maybe write it. So the external field, I will call it, so I will use here the vector potential A, and I will call it vector potential external for the external field. And of course, this is equal to, so it will have some polarization that I take as in the X direction. And within the quasi 1D approximation, this is just all the modes of the external cavity with the corresponding amplitudes, that it's h bar divided epsilon 0, a frequency omega m, the external cavity length, and then this surface, so transverse area of the cavity. Then what else do we have? Then we will have the annihilation and creation operators of excitations outside the cavity. And this I will call B. Okay, and then we will have the spatial profile of the modes, which for this cavity is just a standing wave of the external cavity. And this means that we will have this external profile. And here set is in between L and L plus L external. So L external is the length of the cavity, okay? So of course, these frequencies omega m, I will write it in a second, but they are given by integer multiples of pi divided the length of the cavity, which is L external. So in principle, I could tell you that this is the model for the external field. And the only thing that we have to do is add one more thing, which is that we are going to take the limit of L external going to infinity. Okay, so a large cavity. But what I am going to do now is I am going to show you that this is equivalent to a continuous model that simplifies things very much. And what I mean by continuous is the following. So imagine that we have, well, not imagine that in this case, we have these frequencies of the external cavity, and the distance in between the resonances outside the cavity in this external in this external cavity, it's proportional to 1 over the distance, 1 over the length of the cavity, sorry. But if 1 over the length of the cavity goes to 0, this means that the number of frequencies becomes infinitely dense, okay? The set of frequencies becomes infinitely dense. So you always have one frequency very close to another. So you get to a continuum of frequencies. And this is the kind of model we are going to use. So in particular, now what is going to happen is that when we talk about a sum over modes, m to infinity, when we put here a limit when L external goes to infinity, then this is equivalent. And I remind you now explicitly that the frequencies omega m are nothing but pi c divided L external times an integer m. And therefore, you can replace the sum over modes by an integration over frequencies and of course, because the connection between m and omega is pi c divided by L, you will have here this factor L external divided pi c. Okay? So whenever we have a sum over frequencies or over mode indices, this is equivalent to doing an integration over frequencies with this factor L divided pi c. Now, if we replace sums by integrals, but we still want the condition on the Kronecker deltas to be satisfied, in the sense that if I tell you that I have the Kronecker delta of m prime, and then I sum over m, this is equal to 1. So this is the definition, or one of the definitions of the Kronecker delta, okay? Then if I want this to still be true in the limit when L goes to infinity, then I have to redefine the Kronecker delta in this limit in the following way. I have to say that the limit when L goes to infinity of the Kronecker delta, it's equal to, now what do I need? I am changing the sum, I am replacing it by an integral. So if I want to get a 1, I will need to write in here Dirac delta of the corresponding frequencies, omega and omega prime, okay? So I will call omega to the frequency associated to m and omega prime to the frequency associated to m prime. And then, because we have this factor L divided by C, we need to add here a factor pi C divided by L. Okay? So essentially, this is what we get when we go to the limit in which L external goes to infinity. The number of frequencies becomes, or the set of frequencies becomes continuous, so dense, and then sums are replaced by integrals, Kronecker deltas are replaced by Dirac deltas, and therefore we are going to change. So we are going to change annihilation and creation operators in the discrete modes M. We are going to define continuous annihilation and creation operators that will make sense in the limit of L going to infinity, and they will be given by this. L external pi C B M. Why do we do this? So this is just for convenience, but the idea is that now Bm with Bm dagger, the commutator of Bm with Bm dagger, that's the Kronecker delta. But we are replacing the Kronecker delta by a Dirac delta. And the Dirac delta has this factor here. So if we define an operator B that it's equivalent to the operators B in the discrete, but multiply by this factor, then just from the commutation relation of the B's, we will get the following. We will get that the commutation relations of these operators are the same as we had in the discrete version. So let me write here, then we get this. But now we have a continuous version of it. So now we have commutation relations between these operators, B of omega, that now form a continuum. So now omega is a label, and this label is continuous, okay? But we know that the commutation relation between B and B dagger is a Kronecker delta, sorry, a Dirac delta of the labels omega. So then once we have done this, we can finally write the external quantized vector potential in the following way. So we will have polarization EX. Now the sum over M has been replaced by an integral over frequencies. The prefactor in here now will have this prefactor L external divided pi C. So then overall we get something like this, pi C, epsilon 0, omega and S. Then we will have here the continuum operators instead of the discrete ones. And then we have finally the mode profile in space. Okay, so this thing in here it's our quantized field, and in particular you see that it takes the form of a continuous one-dimensional, because we are in the 1D approximation, quantized field. Okay, and this is the type of fields that appear when you do a canonical quantization in quantum field theory. Okay, without going to a discrete version of it and putting a cavity and whatever. So just in free space, you get a continuous version of a quantized field. And there is one important thing in here. So B of omega, it's important that you understand that this omega doesn't refer to a Fourier transform of anything. This label omega is just a label that characterizes what is the frequency of the field outside the cavity, or what is the frequency of the modes outside the cavity. It's not related to the Fourier transform of some time-dependent function, okay? So in this, it will be even more clear later, especially because here, the operators that I have written, they do not depend on time. I have just used a Schrodinger picture notation in which operators do not depend on time. So you see that this omega has nothing to do with the time evolution of the system. This is just a label, okay? So then now we have a model that makes more simple the description of the field outside the cavity. So now we have been able to put the mirror of the external cavity to infinity. And we have a sensitive description that is very compact and in which everything is well defined by some operators that form a continuum, and they have continuous canonical commutation relations. So now that we have the model for the external field and we have the model for the internal field, because we know that we are assuming it's just a single mode of frequency omega c, we will talk about what happens when you include all the modes of the cavity, okay? But for now, let's focus on a single mode. Then we can move on to write down the Hamiltonian of the full system, okay? So again, just very quickly, our system will be the cavity, our environment will be the external field. And then when we combine them, we get a Hamiltonian that has several terms. The first term is just the free evolution. So the free Hamiltonian. So imagine in particular that the mirror would be perfectly reflecting. Then there would be no coupling between the external field and the cavity field. And therefore, the Hamiltonian of the system would simply be the Hamiltonian of the cavity plus the Hamiltonian of the external field. And that we know very well because we have been doing quantum theory of the electromagnetic field. And in particular, I will write it in this way. This is the free Hamiltonian has a contribution from the cavity and a contribution from the external field. And in particular, the Hamiltonian of the cavity will be equal to just the free Hamiltonian of the mode that we are considering. And then the free Hamiltonian of the external field, it's equal to h bar omega for each mode. So h bar omega b dagger b for each of the modes that form the external field. And the only thing is that here, instead of a sum over modes, we have the integration over modes. Okay? So this describes just the free evolution of the fields. And now we need an interaction. So the interaction, I am going to write it down and then I will convince you that this is the right interaction. So the interaction is very simple. In principle, it takes this form. So the interaction between the external field and the cavity field, it cannot be anything too different from this expression that I am going to write. So let me write it down and then we discuss it. Okay, so this Hamiltonian here. So let's discuss why this Hamiltonian and not any other. So first of all, so let me understand what this Hamiltonian is saying. This Hamiltonian is saying something very simple. It's saying, okay, the processes that are contained in this Hamiltonian are, I can remove one photon from the cavity. So I can annihilate one photon of the cavity and create one photon in the environment. Or the opposite, I can annihilate one photon from the environment and create one photon inside the cavity. So this is describing single photon tunneling from the external field to the intracavity field or from the intracavity field to the external field, okay? On the other hand, this minus sign and IH bar and so on, that I am just taking for convenience, but you could put here a plus sign and remove the I, or in general, put any phase, okay? This phase, it doesn't play much of a role. It doesn't play any role at all, actually. So now, what this is saying is that you can destroy one photon or create one photon at a specific frequency omega. And each of these processes will be accompanied by some kind of rate, some kind of coupling rate. And this coupling rate, in principle, it can depend on the frequency. So different frequencies will have a different probability of being converted from a cavity photon in the mirror. Now, why do I write this one? and I don't put more terms. So why not, for example, also put pairs of photons that leak from one to the next and, you know, all these things? Well, that we know from the previous chapter. What is this mirror? Is this mirror a nonlinear material? In principle, you could make it of a nonlinear material if you want, but if you just want a mirror that simply allows light to go through and so on, usually these materials here are linear. They do not have nonlinear physics, nonlinear optics related to them. And therefore, we have learned from the previous chapter that the energy contribution that a linear material has on the Hamiltonian, it's always quadratic in the fields. So it will be quadratic in the electromagnetic field. So if it is quadratic in the electromagnetic field, it means that it will have only combinations of two operators, okay? And of course, because we care only about the interaction, it will be a combination of operators of the external field with operators of the internal field, okay? Now, why this specific combination, B dagger A and BA dagger? Energy conservation, also from the previous chapter. We know that the combination, for example, B dagger, A dagger, would be suppressed by energy conservation. So as long, and this is the important thing, as long as the interaction is just a perturbation, okay, as long as the interaction is just a perturbation, then again, within the rotating wave approximation, we know that any quadratic process in which you simultaneously generate photons at frequency, so of the external field and the internal field, that's violating energy conservation. And therefore, that will not appear in the Hamiltonian. So essentially, this is just my way of convincing you that this Hamiltonian is the most general Hamiltonian that you can think of for the interaction between two fields going through a partially transmitting dielectric, okay? So essentially, this is what I want to convince you of. And then let me also say, well, let me first maybe give some kind of name to this Hamiltonian. This Hamiltonian is known as the beam splitter Hamiltonian. So I have mentioned this kind of Hamiltonian sometime in some comments, okay? And beam splitter refers just to this fact that you take one excitation from one mode and you move it to another mode, okay? So each of these Hamiltonians for each omega is called a beam splitter Hamiltonian. So this is beam splitter Hamiltonian. And as I say, it comes simply from the most generic assumptions, which are that the medium is linear. So it has no nonlinear optics. It doesn't have nonlinear optics. And energy conservation. Okay. So now this is the interaction Hamiltonian that we are going to work with, but we are even going to do a couple more approximations. So the first approximation is the following. So let me write it down. Let me see how much space I need. Okay, maybe I can do it here. So let me just write down a couple of things first. So as I said, because I just said them, but I want you to have it written and remember. This Hamiltonian describes tunneling of photons through the partially transmitting mirror. So also, as I have mentioned, we are assuming that the interaction is just a perturbation. And in this context, as you will see in a second, but in this context, it simply means that the optical frequencies that are the scale of energies for the H0 are much larger than the tunneling rates. So G square of omega, okay? And most importantly, this tunneling rate, G square of omega, this is proportional So I'm not going to give you the exact expression, but you have it in the notes. You can derive how this G of omega depends on the physical system parameters, but it's very intuitive that it is proportional to the transmissivity. So to the transmissivity T at frequency omega. So the transmissivity of the mirror, so how much energy it allows, okay, how much intensity it allows to go through for a given frequency omega. And of course, we are assuming that this is very small. I mean, so the cavity is open, the transmissivity of the mirror is not perfect. So the reflectivity of the mirror is not perfect, but it's still a pretty good mirror. So maybe it's 99% reflecting or 90%, but it's certainly not a bad mirror, because if instead of a mirror is just a dielectric that allows light to go through, then you cannot make a model in which you simply have two fields were separated and slightly coupled by a small interaction, okay? You need to do a quantization of the electromagnetic field subject to all the boundary conditions of the Maxwell equations and so on. So then we will assume that the reflectivity is very large, so the transmissivity is very small. Now, there is an important thing, which I have already mentioned, but here I want to make it even more clear. So energy conservation will tell us, so I already used energy conservation to kind of remove from the possible quadratic terms, the terms that are B dagger, A dagger, but even these terms, B dagger, A, if the frequency omega is very different from the frequency of the cavity, omega C, the corresponding mode will not do anything. They will not contribute. So this integration from 0 to infinity, actually, the only thing that matters is frequencies around the cavity frequency, okay? So let me write this explicitly. So out of all the frequencies, only the omegas that are close, okay? And we will see what close means exactly to the cavity resonance will contribute. Okay? This allows us to do two very important approximations. First approximation is that the transmissivity of the mirror, I said that it depends on frequency, but in general, mirrors are made such that in a large bandwidth of frequencies, they have the same reflectivity. So you don't want a mirror that, you know, for, I don't know, like 400 nanometers, it's 99% reflectivity, and then for 401 nanometers, it's 80%. That would be crazy, because just changing a little bit the light frequency or the cavity length would change completely your physical system, your physical setup. So then T of omega, we can assume that it's basically independent of the frequency, okay? And this implies, because the dependence of the coupling G, it's through the transmissivity, this automatically implies that G of omega is actually, or can be taken approximately, as a frequency independent function, okay? Just the coupling at frequency omega C. And this is what we will call square root of gamma over pi, okay? For you will understand why gamma over pi. And we will assume that this is the case for frequencies that are, let's say, between the cavity frequency minus the coupling square and the cavity frequency plus the coupling, okay? So in particular, what I am saying is that the coupling G, in particular the square, that determines what is the width of the frequencies that couple effectively to the cavity. And we will see that all these things are self-consistently correct. Okay, so essentially the next week, I will take on from here with these approximations. We will simplify the interaction Hamiltonian, and then we will proceed to find the evolution equations only for system operators in the Heisenberg picture. And you will see that this will give us a very interesting model where dissipation appears very naturally, and where we get some kind of generalization of the Heisenberg equation of motion that we can use to describe real physical systems that are open. So for now, I think that we can leave it here. It's already 3:40. And if you have any questions, we have 5 more minutes. Let me maybe stop already the recording